Hey guys out there. You guys hear me all right? I think we're doing much better this week than we are last week. Now that we got Smarky's been over here, we got some hardwire run over to this streaming computer. Hopefully I won't have any Wi-Fi problems. I think the live stream was a bit much for the old Wi-Fi card. Smarky was making fun of me for having that thing even plugged into the computer. Okay. Take a peek. Mark. Pryor's here. Fender's here. Smarky. Excellent. Got me. Excellent, guys. I don't know what the delay is like. Everyone seems to be over on YouTube. Okay, a couple people over on Twitch, a couple people over on YouTube. Cool. Anyways, I know I posted in Buffalo Multi-Rotor at Smarky. He's been over here. He's been over here at night. We've been working on a little project, and I guess we're okay to take a look at that. There we are. All right, so what we are doing is we are making canopies to fit the raggy frames. And Smarky, he knows more about what particular model these are for. But anyways, we're trying to figure out a good way to make a lot of these as if you're going into production, right? So printing is easy, you know, load up the STL file, throw it in the printer, and 5 hours later, you got a part like this. All right, but the problem is Smarky'd like to make, 10 of these, in a time efficient manner, right? So if these take 5 hours each to print, then making 10 of these is gonna be a nightmare, right? We got one printer, you got a couple $100 into your printer. You certainly don't want to buy 10 printers. We're not looking to start a 3D printing farm or anything like that. We just want to make some of these canopies, right? 72. Right, we do eventually got to make 72 of these. And it would be great if we could make 1,000,000. That's right, Mark. Mark and Mark. All right, so I guess here, I should say, the first one we did, this guy, Smarky printed. It's out of TPU, so she's flexy, right? Some purple TPU. All right. This would be the ideal canopy, right? It's enough protection for your camera and your electronics, and it's got a little bit of give with that durometer, so it can take an impact from crashes. And this particular one has a little mount for a session on top of it. What we're gonna do, and what I've been teaching Smarky all week, is how to resin cast these guys. So rather than taking 5 hours to 3D print them, we're going to take 5 minutes to cast them. All right, so we're gonna be attempting to cast these out of like a medium durometer urethane. So they'll have the same properties as the TPU. They're going to have a little bit of flex. They're going to be really durable, tear resistant. Think of like your rollerblade and skateboard wheels. Those are made out of different durometer urethanes. That's the material that we're working with. So this one here was Smarky's first attempt at a master, right? So this is printed out of ABS and then was vapor honed with acetone to give it that nice smooth surface, because we're going to be making a mold from our first part and then duplicating that first part potentially a couple 100 times. So this part here has to be exactly how you want it, because you're going to be stuck with it once you make the mold from it. So you spend a lot of upfront time, you know, and you're not just hitting the print button and waiting 5 hours. You're going to spend a couple days on the master part, getting it just the way you want it and getting your mold just right. But then after that, you can start banging these out, you know, every 5 minutes you can have a set of these. And with the urethanes, we've got a bunch of different colored dyes that we can mix into the urethane, so we can make any color, a whole bunch of different opacities, you know, so you could have it see-through, see-through with a little bit of a tint, or fully opaque. Here's one I printed. So this is just ABS. That's probably too bright to see, but this is just ABS straight off the printer before cleaning up. And this hasn't been vapor honed. What I would do after this is go around with sandpaper and files and clean it up and get it like a finished part. The vapor honing didn't work. This one, we didn't end up making the mold from this one because the vapor honing was too aggressive. So the part kind of melted on us, right? So it deformed a little bit in the corners. It slumped down, and it kind of made a brim on here from slumping down. And so we decided to set this guy. I mean, you know, the surface is great. The surface is super smooth, glossy. That was really good, but there's a little bit too much distortion going on with this part here. So we put that aside, and the master part is actually in the mold right now. We're doing a silicone mold, all right, and it's a 2-part mold, and our master's in there right now, and it's drying. Another ABS part, and we had Smarky sand it down, you know, run through the grits, 100, 220, 320, get the part nice and smooth. Then I went around and cleaned it up with some needle files. Got it to where I thought it was, you know, looking pretty good. And then what we did was we primed it and spray painted it with a texture paint to give it a little bit of that orange peel, because these are going on raggy frames, and the raggy frames have that kind of orange peel texture on the top surface of the HDP. So I sprayed some of the texture paint on the ABS part to match that and to hide some of the little areas where we lacked a little bit of sanding in the nooks and crannies, right? So we're trying to be efficient with our time. Anyway, so we did that, and let me pull up some pictures that we took while we were working on here so I can describe that. So switch over to my desktop here. There we go. And there. Okay, hopefully you guys can see that. All right, so here's Smarky mixing up the first batch of silicone, right? So this is a real soft silicone that we're using, which will make it real easy to demold our part. There's a little bit of an undercut in this part, and there's some through holes in this part, which are going to be tough because the silicone's going to want to grab onto those when you're casting your parts. So I'm going with a kind of a soft durometer. It should be fairly easy to separate the castings. You know, the material's soft enough to bend out of the way. If you were using a really hard durometer rubber, the way that this part is designed. Oh, I gotta get out of my way. Get out of my way there. Okay, the way this part was designed, if you used a super hard rubber for your mold, you probably wouldn't be able to pull the part off of the mold because it would catch on the inside of this thing. Right? So we're using a soft urethane. And there's Smarky mixing up our first batch. Let's see. Step through these. All right. He decided to go with the pink silicone. That was his favorite color. Anyone that's seen some of his some of his quad builds. Know that he likes light blues, purples, and pinks. Here is the master. That is our master part in an out of focus picture, sitting at the bottom of this little box that we built. The box is a throwaway piece, right? So it is constructed out of real simple, just with some leftover flight test foam board, right? That we brought back from Flight Fest this summer. Thanks to John Kinkle, he was able to snag a couple sheets for me. And so we built this little four-sided box, hot glued it down to a piece of pine, and then we stuck our master 3D print down into that box. The holes in this in that 3D print are all backfilled with plasticine, your like oil-based clay. It's a clay that doesn't dry, and it also doesn't stick to the silicone, and it also doesn't interfere with the silicone curing. Because this part is hollow, right? And we need to do this mold in two parts. So I've filled the inside of the part with this plasticine clay, and then leveled it off in the camera opening, and I've filled all the little screw holes with a little bit of plasticine, right? That's to make this thing easier to pull the mold apart. And we're probably going to just chase the finished parts with a drill bit. You're just going to kind of do a final ream of all the holes when we're done, and you'll have your finished part. But anyway, so there's our little textured part sitting on the bottom of the box, and there's a view of our gorilla doing his stirring. Very, very good stirrer. I don't know why he looks so big on these pictures. Must have been the lens I'm using. All right, so here we go. So now I'm pouring the silicone into the mold here. We've mixed it up. Didn't do any vacuum degassing. We should, but this is like a 24-hour cure time for the silicone. It gives it enough time for those bubbles to rise to the top. So not super critical. You definitely are rolling the dice a little bit by not vacuum degassing it, but if anyone's seen my barn, you would understand why I could not find all the tools required for me to vacuum that silicone to get all the air bubbles out of it. So anyways, here we are. We're pouring the silicone into the corner of the mold. I've got my hand under the opposite corner, tilting it slightly, right? And I'm pouring the silicone into the lowest point in the mold, and you pour it real slow, and you let the level of the silicone rise up. And yes, thank you, Mark. Thank you, Digital Silence. Anyway, so you start pouring this. You got to do it nice and slow, and you got to let just the level of the silicone build up really slowly across the part, so that you don't trap any air bubbles in any of these little pockets and holes in the part. So anyways, up we go, we fill it, and there she goes. We got our little box filled up. Now this is just all hot glued together. You got to, you make sure that you don't have any holes. Otherwise, tomorrow morning, all your silicone will be all over the table. So you got to make sure she's watertight, and you let this guy cure for 24 hours. And there we go. This was a couple hours ago. Smarky came over, and we did a little drum roll and popped the part out. Smarky's good at going slow. Havelock, yo, what's up? I think later we're gonna get to a little CNC programming. Havelock. So right now we're going over the silicone molding that we're doing for the raggy frame canopies. All right, so we're not gonna 3D print these. I know you're here, Smarky. That's why I'm taking little shots at you. Anyway, so here's our master part. Popped out of the mold. She came out real nice and easy. That was good. It's like fingers crossed if you accidentally glued the thing in there or not. But she slid right out. Super easy. There's a few undercuts on the part here. So if you can see my cursor, the little fin that's on here, there's a pretty good undercut there. And what an undercut is it's an overhang that is going to make it really difficult to pull the part out of the mold. But like I said, we went with a pretty soft 30 durometer silicone here, and just with a little squeeze, part came right out. So next step is I gotta push all the plasticine clay back out of the part and get it cleaned up. And let's see what our next picture is. Okay, there we go. So I've got my my first half of the silicone mold ready. I've went around with an X-Acto knife and carved this little notch into it. What's that's going to do is register the two halves of the mold together. And I've cleaned up all the plasticine clay out of the master. And the master part is going to go back into the original mold. There she is. You can see the red ABS that Smarky's using. So the part is now back in there. And the next step is going to be building our gates and our vents. So we need a place to pour the casting urethane in, and we need a way for the air to escape out of the mold. So those are the two things: urethane in, air out. All right, so there we have some plasticine clay rolled into a little dowel, and it is sitting off to the side of the part, somewhere nice and easy to break that piece off and, you know, go across it with little snippers, and you can kind of pop all those little pieces off of there. Each one of these little toothpicks that you see is a vent for the air. So what we're gonna do is we're gonna fill this whole thing with silicone, and then when you go to make your final urethane part, you're gonna be pouring your urethane into that white column sitting there. That's some clay. That's gonna end up being a void in the end when we pull all this stuff back out. So you pour your urethane in there, and it's gonna flow down into where the part is, and the air is gonna go out those toothpicks. So here we got Smarky mixing up another batch of that delicious pink silicone. Havelock, your threader chipped out. Well, not a good idea to turn your back on the machines. Where's Marty? Oh, Marty just sent me a video of somebody whipping like a 20-foot bar on the bar feeder of a lathe at the shop. And I'll tell you, I don't know what those lathes weigh, 30,000 pounds, but that thing was dancing around the floor of the shop like a broken washing machine with this huge 10-foot section of bar hanging out the back of it. That was awesome. Anyways, so here we go. We mix up another batch, we pour it in there, and there we are. You can see how this, hopefully you can start to see how this is going to work, right? The silicone, Soren, the silicone came from Smooth On. It's Mold Max 30 is the durometer that we're using here. It's like $100 for a gallon setup. And I think we probably burned through about half of it. So that's Smooth On. If you get into like props or anything like that, dude, they've got everything. Everything you can imagine. They got all the casting urethanes, the silicones, foam. If you're into cosplay or makeup, they got all the stuff for working with body casting and prosthetics and stuff. Very cool stuff. Here's the final. This is the second half of the mold that's poured, and it's sitting on the table behind me right now like this. Tomorrow we're going to be able to pull the two halves together, get the master part out, clean out some of that clay, take the toothpicks out, and what we're going to be left with is the cavity of the original part. And we'll put the two silicone halves back together, and they should register on that little cutout that I made with the knife. And then we're gonna fill that guy up with some urethane resin, and hopefully we have a good part. I've got a bunch of different durometer urethanes, and we're gonna experiment with what's the ideal stiffness of this part. You know, is it better to have the part really soft, Is that the best approach? Is it a good vibration damper for the camera? When you hit something, it just gonna collapse and that's gonna absorb the shock, or is it better to have a rigid urethane that just has just the slightest bit of give, um, in order to keep the electronics safe, right? So you don't want to smush too much and end up damaging your boards on the inside of the part. But if we used a completely rigid urethane, then if you smack something, the part's just gonna shatter. 80, I was 80 durometer, 80. I was going to start with a 72. So that's pretty close. Matt Fender said, are we going to use 80? I think we're going to use 72 to start with. It's I got like a whole gallon setup of it, of tintable. It's clear. It's like a clear amber, and then you can tint it whatever color you want to. And it's 72. Let me see if I can bring up Smooth On website here. So Smooth On, the urethane came from Smooth On as well. Here's the silicone rubber. We're using a Tin Cure silicone rubber, nice and easy. Mold Max is the rubber that is the silicone that we used for the mold. And Mold Max 30, right? So that's a 30A hardness, so it's fairly soft. You can go even softer than that, but you got to remember, the softer you go, the easier it is for that mold to deform while you're casting. So you got to have a good balance between how rigid your mold is and how easy it is to get the parts out. And for the urethane, go back here. Urethane resins, probably smooth cast, 72 clear amber. This guy, I believe, is what we're using. Smooth cast 326 color match. Yep, it's a color match series. That's right. So this is what we have. It's a 72 durometer. If you don't tint it, you get this amber clear part out of it. But like I said, I got a whole a sample kit of all the Ignite colors that Smooth On sells, so we can make it whatever color we desire. It's just gonna be up to coming up with a formula of which pigments we're gonna put together. Let's see, Havelock, so many choices with plastic, crazy. Oh yeah, like the urethane. This is just our urethanes, right? We'll go back up. You've got two major categories for silicone rubber: Tin Cure and Platinum Cure. One of them cures based on moisture, and I'm not too familiar with the benefits of each of them. I've used both of them in the past, and they both seem to work just fine. Urethane rubber, polysulfide rubber. Urethane, this would be like your urethane plastics, epoxy plastics, putties, expanding foam, adhesives, life casting, so that's for use up against the skin, and it goes on and on and on. Dive into your urethane plastics, and you've got this series, right? We've got a whole bunch of durometers, right? From 45D as our softest up to 85, it looks like. That's going to be pretty stiff. If we come down here to task series, yeah, all these, I mean, you got to go through and read all the data sheets. It's crazy. I mean, they're all for very specific, purposes, right? You can spend all day trying to figure out which one you're going to use. I got a whole bunch of different ones that we can test out too, so it'll be a good time. What's nice though is that the stuff here, like you read your cure times. I don't know if you can, if the resolution's good enough, but you've got cure times, 10 minutes, 5 minutes, 30 minutes, 10 minutes, what else? 15 minutes, right? So you can get your cycle times up real high. You mix up a batch, throw it in there, and 10 minutes later you can pull the part out of the mold. right? So you can kind of keep up. You can start to move into production that way. We started with just a one piece mold, right? Want to work out all the bugs because I don't know. It's been a couple years since I cast anything, and so there might be some surprises. So I started off with just a one piece mold. But if you really want to ramp up your production, simple. You just take and make a new mold and put as many parts as you desire in that one mold, right? So if you're looking to get higher production, print out 5, print out 10 canopies, put them in a circle, like make a nice little array of canopies, and pour your silicone over the top of that. That way, every time you cast urethane into that mold, you get 10 canopies, right? So 10 minutes, 10 canopies. So the more productive you want to be, just the more original parts you're going to shove into that mold. Super easy once you're up and running. All right. So anyways, back to there we go. That's smooth on stuff. I'm a big fan of that stuff. That the last picture? Yep, that's the last picture. So that's where we left off. Okay. Maybe we can come over here to SolidWorks. We worked on the part in SolidWorks because all I had was an STL, so we actually redrew the part in SolidWorks. And there we go. So I redrew it so that I had a parametric model instead of just a wireframe, so that we can work on hole sizes and position. I wanted to work on undercuts. The original model had a lot of undercuts, so it would have been really difficult to pull out of the mold. So I redrew it and tried to get rid of any parts on here that would be difficult to cast. And SolidWorks has a lot of features to even check to see how you're doing. So I can select a plane and I can see these red areas are the areas that the mold is going to get stuck on, right? So you can see I have a couple spots back here that the mold is going to want to hold on to. And I got some spots here that the mold is going to want to hang on to. So that was our reason for using a real soft durometer silicone, because we'll be able to pull the silicone out. The silicone is going to give enough to let go of that part. If we use a really hard silicone, not going to want to come out of there. All right, and if I change my direction to look at the top, so green means we're pretty good. The mold is gonna, it's gonna come out fairly easily, but you can see there is still some parts on here that are going to want to hold on to that silicone, right? So those are the parts that we have to pay attention to. Anyway, so there's the reason behind using a pretty soft silicone. So there's our part. What else can we say about it? In order to determine how much resin we needed to purchase and how much we needed to mix up in each batch, and let me tell you, we were dead nuts on with both pours. SolidWorks is feeding all that information to us. So here's our part. We go over to Smooth-On's website and we go to the material we're using, and we come down to the technical data here, which might be hidden for you guys there. So here's our technical data, and we come down and find out that this stuff weighs 1.07 grams per cubic centimeter, right? That's how much that material weighs. Once we know that, all we got to do, come over to this part, and we evaluate the part, and I tell it that the material properties are 1.07 grams per cubic centimeter. You could see SolidWorks did some conversion. It converted it to grams per millimeter. But anyways, so you type in the density of the material, and SolidWorks comes back and tells us how much that part is going to weigh. see if I can change this to grams. Okay, so that part is going to weigh 25.3 grams in urethane. So when we go to mix up our urethane to cast that part, I know that I need 25 grams to fill the cavity of the mold. We're going to mix up extra. We're going to mix up about 20% more material because you lose material on the inside of your cup from when you're mixing and you pour it out. Some of the material gets left behind in the cup. And then we want material to go up the vent as well. So we're going to mix about 25% more material than that. And we'll be dead nuts on. For the silicone, all I had to do was draw the box. We made a 5-inch square box. So I came into SolidWorks, drew a 5-inch square box like that. Okay. And then we subtracted the part out of it. And let's see if I can illustrate that for you. There. So it might be hard to see, but I have the part is subtracted out of that big cube. And all I have to do is come in here and same thing as before. I select the part, let's say the top half, that was the first pour that we did. Come over here to mass properties. I come in, I go to smooth on, look up the weight, I type the weight in here, and it tells me that that half of the mold is going to weigh 1.4 kilograms. So again, I overestimate by about 10%, figuring that we're going to lose 10% of the silicone to the inside of the mixing cups. And the silicone has a 10-to-1 mix ratio. So I mix up 1.4 kilograms of silicone and let's see, 140 grams of hardener, right? 10-to-1. Mix those together, pour it in, and I said I gave myself about 1.5 inches above the part. Dead nuts on. Same thing when we went to pour the second half. Went in, measured the weight of the second half of the mold, 0.5 kilogram. I rounded that up. We ended up doing like 0.8 kilograms, so 800 grams. So we mixed up 800 grams, poured it in, perfect. Just the exact amount that we were looking for. So anyways, that is my 36-minute tutorial on casting. Silicone, right? 3D printed to silicone mold. And tomorrow, hopefully tomorrow or Saturday, we're going to be casting our first urethane part out of this thing. Hopefully everything goes well. All right. Let's see the other thing we got. Oh, here's the raggy frame. I know Havelock, if you're still there and not fixing machines, Smarky, you can see we kind of have the raggy frame blocked out right there with the new canopy sitting on top of there. And we're checking the prop clearance to the side of the 3D print there. You know, making sure our holes were good, making sure our clearances are good. And anyways, that's a little side project. So back to what we were doing. Let's open up that 4-inch build that we're working on here. Live stream quad. Havelock, what's up? Still there? Machines are running smooth? Nothing's crashed? Let's see. Let me catch up with my chat here. Havelock, lots of choices. Fender, D is pretty hard. Yep. He was thinking 80A. 80A. I don't know where the crossover point is. In my head, I don't know. Because the A, when you're talking about your shore hardnesses, yeah, there's the A and there's the D. And there's more as well. But anyways, they do cross over at some point. So 80A is equivalent to something in D. Maybe like a low D value. But yeah, I want it to be fairly rigid. I want to say that the TPU think we looked it up. We looked up one of the brands of TPU, and I want to say it was like 75D. I don't know. Maybe Smarky remembers, but hopefully it will be fairly rigid. I know that silicone was A, super soft, 30A, very soft. Makes you miss school. Yeah, this is quad school. That's what this is. Actually, it's anything school. I mean, quads doesn't matter. The silicone stuff. I was using doing the same thing when we were building the arcade games. Same techniques, casting parts out of that stuff before sending them off into production. I'm sure I know there's a couple guys from Fisher Price that are around in our group. Same deal. I know that those guys monkeyed around with the same stuff over at Fisher Price, making the prototypes and stuff like that. Marky, back? No, we just finished up our little tutorial on how we on where we're at with our silicone casting. People are printing people are printing with low infill and fairly thin walls and stuff like that. So like Fender's saying that he doesn't think the TPU is that hard, but like if you print a solid piece and it's 5mm, 4 or 5mm thick, it's actually pretty stiff. I know I was trying to print a battery strap for my AI quad, and I had to get the material down to like 1mm in order for it to be like stretchy enough to pull it around a battery. Because if it was like 1.5 millimeters thick or 2mm thick, forget it. It wouldn't stretch at all. I couldn't stretch it over the battery. But once I got it down to just like 3 or 4 layers at like 0.3mm layer height, just like around 1mm, then it had just enough give in it so that I could stretch it over the battery. So I think, a lot of the parts, I don't know, they're printed with pretty thin walls. This part here, up at the camera mount, it's at the opening for the canopy or for the lens, it's soft. It's nothing like the silicone that we casted, that's for sure. But like down here where it's thick, I mean, it doesn't bend. I mean, it's pretty rigid. It's pretty stiff. So the problem is that all these 3D printers, all these guys online selling this filament, not very many of them provide detailed specs on what it is that they're actually selling you. So we went back to the website to look up what this was, and they had zero information. It's just listed as TPU flexible filament. There was no indication of how soft it was or anything like that. So I don't know. I went over to NinjaFlex's website and looked up their two durometers that they have. They've got a real soft one and then a medium stiffness. We were looking at the Tokyo canopies. I don't know. I never like held one in my hand, so I don't know how hard they are. Miko would probably be able to tell us if he's got one of the molded ones, the finished molded ones. Jerry has one as well. Yeah. I don't know if I don't think I've ever seen the molded ones. I've seen the like initial 3D printed one. I'm curious as to what technique they were using to get theirs, because on their website they're saying that it's injection molded, so their quantity must be pretty good if they're going to injection molding. But injection molding would tell me that it's probably a more rigid part and not very soft, but I could be wrong. Oh, excuse me. So what's up, guys? Are we back to our 4-inch racer? Back to our 250 gram build. I feel like I'm having more fun with the silicone molding stuff. I enjoy that stuff. It's cool. I think we need to do the same thing on this guy. No, we don't. I take that back. it's too much work. We're just gonna 3D print parts for this. I know we were trying to figure out where the camera's going. I think that's where we left off, right? Before my Wi-Fi card crapped out on me. We needed to find a place to put this camera so that we can design a 3D printed part to mount it to. And perhaps a 3D printed set of knuckles for the motor protection instead of jabbing the carbon fiber. Especially with the bando coming up, you're going to want a little bit of protection on your quads because those concrete walls in the bando are not going to be forgiving on these machines. There may be carnage as you guys start pushing each other. It's going to start off all good, but it's going to turn into mayhem once everyone really gets into that race mode. I can just imagine. I know how Havelock gets into race mode at R&L. You start seeing red, and that's all you can do is just be the fastest guy. It doesn't. Nothing matters. Quad gets destroyed. Doesn't matter. All that matters is winning. OG Shrike, or use roll cage plates like Cerebus. Yeah, I wish I could picture all these off the top of my head, but unfortunately I cannot. So you guys are gonna have to tell me where's the best place for that little guy. Where it sits right now, I don't think that we're gonna see much propeller. The camera's kind of above the plane of the props there. Maybe it catch just a hint of them. To me, I was thinking you got the wiring harness has to come out of this header right here. That's where the wires are going to come out. So we either got to get the wire harness kind of up above or down below so that our wires can like pass through, you know, enough room to loop them around or go right into the stack. One of those two things is going to have to happen. I'm thinking just the easiest thing is going to be to kind of position that camera right around there and then extend the carbon fiber plate out, and maybe we can do something cool with the tip of the frame here, and that'll protect our camera from some strikes, right? If we get that out past the lens. Soren says, am I the only one without audio? Perhaps. I don't know. Everyone else I think is hearing me okay because I'm not typing in the chat. Let's see, we got people in Twitch and we got some people in YouTube as well. Let's take a look. I don't know, how's YouTube? Good audio on YouTube? Okay. Like I said, I'm monitoring it in my headphones, but I don't know, I don't always get all the settings right. Digital silence, you can hear Fender, good. Alright. Yeah, it sounds like, yeah, I think I've got guys on Twitch and guys on YouTube that can hear. So it might be on your end. Let's see. Okay, so we good? I'm gonna run the camera here. I know this is a community build, so if you guys really need to override my decision here, go ahead and override my decision. But I think that's gonna be, it'd be a decent spot for it. Real easy to, we'll 3D print like a little recliner for it, and then we can kind of move on to some of the other things that we need to get to on this quad. Let's see. I wanted to extend that. Here I popped over into my frame. Hello, there we go. And I need to refresh my memory on, I had no audio until I went on Twitch. Well, Fender, you're over on YouTube, right? Fender, you got audio? Sorry, okay. Refreshing my mind, because we drew this like 2 weeks ago now. We had a crappy internet connection last week. So we're going to extend this frame. I only want to extend it forwards though. So let's roll back our frame design. That's what's great about using these programs, is that we can travel back and forth in history here. All right, and I'm going to add material here. I'm going to grab the plane that I was drawing on, and I'm going to do an extrude operation, and I'm just going to draw a rectangle. Kind of lock it onto the two corners there, and give myself a measurement. And let's say 10 millimeters of extra frame out front. And our thickness, I want to make it always match the thickness of the rest of the frame. There we go. Now rolling it back, and I have a little bit of a warning saying that this fillet has an issue because the corner is missing. Go back and edit that. Hey, there's missing items. Yep. I just have to tell it what I did. Yep. Okay, now our fillet's fixed, and we've extended the frame forwards just a touch, and I think we can maybe even machine down into here, into the front part, in order to make it real easy to attach the camera mount. Ben, what's up? I didn't know you were in here. Shorten the strap slots, since they can only be as wide as the stack bolt interspacing. Yes, that's right. It would certainly make, yeah, Ben's talking about our battery strap slots that we drew. And making these shorter would make the frame stronger at the root of the arm. And he's right. So if we go back over to our assembly here, and if we feed a battery strap through here, the easiest way to do it is to go through the stack, but it's a narrow channel. And so if we find a battery strap that fits there, this slot is unnecessarily big. My thought is that we may end up going over the top of the stack with the battery strap, with a full-size battery strap. So if we 3D printed a little cap for the top of the stack that we screw into, like a little, let's say a little TPU dome, and when you're screwing the stack together, like there's our, hide our battery. All right, here's your screw coming up from the bottom of the frame. Get through all your standoffs and then screw into your cap and suck the whole assembly down. That the way we design our cap could be a nice little arc that lets the battery strap kind of contain everything. I don't know if that's too much, if we risk like damaging our stack in a crash with the battery strap running around it. Not sure. I haven't given that too much thought. Let's take a measurement of how, look at how distracted I am. Take a measurement of the width in here. 14 millimeters. So we would need a battery strap 14 millimeters wide in order to get through that strap. And I think I've got some Velcro behind me. Okay, these crappy little things. I don't think you'd ever want to use this, but let me just take a measurement here real quick and see what these are. These are 10? These are 10 millimeter wide. So there are options, although I wouldn't recommend using this. I would imagine that these would break in a crash. They don't have anything like nylon running through them or anything to keep them from separating in a hard crash. It would work in a pinch. But we got 14 millimeters to work with. Yeah, you see what I'm saying? We could draw that. That'll be one of the 3D printed parts. We're going to have to find a place for that receiver. We got to find a place for our video transmitter. Let me get my battery back. There she is. Okay. you can weave it. Go in the slot. Fender says weave it. Go in the slot from the top, then under the frame and out the bottom. Does that... Yeah, you're right. Fender's right. That's exactly what you could do. Let me see if I can get a cross section here. Yeah. So what you could do, like Fender is saying, is you come around your battery and come around the outside of the frame and then through the slot from the top. And then you'll come across and up out the slot upwards and around the outside of the frame and cinch it down. So you have a little bit of wobbly battery because you're sitting on just that one little point. So if we do that, and I think it's a good idea, I think we 3D print like a little battery tray in order to give ourselves a high point in the back of the battery and a high point at the front of the battery so that you can get a really good grip on it and the battery will be nice and firm and it's not going to want to rock on the battery strap. And that'll be perfect. That's a good idea, Fender. Exactly right. That's the way we got to go. And then we don't have to 3D print a canopy and monkey around with any of that nonsense. Benny Mac says he's using a 15 millimeter wide Duralock for grip. Yeah, does the Duralock have like a silicone like silicone screen printed onto it for grip? I had to take a drink. My throat's getting dry. Okay. Let's see, does that offer us enough protection? I think so, right? We tuck the camera back a little bit. It's our camera. Uh-oh. I just sent my camera to outer space. Yep. That was silly of me. There we go. Okay. Pull it back. Perfect. I like it. Dualock. The polypropylene Velcro alternate. Oh, Dualock. Not Duralock. I use the Dualock from 3M on a whole bunch of stuff. All my small batteries I hang with Dualock from 3M. I think anything 500 and under, that Dualock will hold on to the battery unless you smack something really hard. You don't even have to run a battery strap around the battery. Just the Dualock to, you plop the battery onto the bottom of the frame and you're good to go. Yeah, you got to put, a strip on your battery and a strip on your frame. Yeah. Like I'll peel the label off the battery and then just kind of clean it up with a little acetone and then stick the Dualock on the battery and yeah, it doesn't come off. I mean, it kind of can wear out after a little bit, but man, that stuff is tough. It hangs on for dear life. Let's save this assembly here. And let's insert our camera mount part. So for our camera mount, I'm going to start a new part. This is going to be just a virtual part. I'm going to pick my front plane, anchor it to. And let's draw a rough outline of where this ramp needs to be. So where's my part? Okay, this little blue part here, that's my part. It's empty right now. I'm going to draw on the right plane. That's the direction I'm looking at. There's the right plane. That's the plane I'm going to draw on. And I'm going to give myself a little sketch. Hopefully this is like a part that will be real easy to 3D print. Start here. And we want to come up and hit that thing. So we'll like come around like that. And back down. Frame. over. See, Smarky, you're back. Smarky, you keep saying that. Where do you keep going? Smarky says he's back. Welcome back, Smarky. Nice to have you here. It's always a party when Smarky's here. Inches. You don't want no stinking inches. We're gonna catch up with the rest of the world real quick in one click. Millimeters. There we go. All right, 4mm. Woo. 4. Go. Gonna take this little center of my circle here and snap it to there. Sure. That looks all right. College and SAT stuff. Oh, Smarky, which one's better, YouTube or Twitch? I see you're on both. You're playing both. You're screwing up my viewer count. Actually, you're padding my viewer count. I like it. Keep it up. Let's see. All right. I'm going to extrude my sketch, and we need to be wide enough in order to catch that camera. 24? 4mm wide? Sure. Okay. I can see what's going on, but it might be tough for everyone to see. So there we go. This is a little thing that we just threw out there. That's going to end up be our 3D printed, our little 3D printed part. Whenever you're doing a 3D printed part, the way I look at it is I hate support material. So when I'm designing my part, I design it right from the beginning to either eliminate or minimize the amount of support material that's going to have to print, because cleaning up that stuff is a real pain. The TPU is real sticky, real hard to get that stuff out. I hate it, right? So this part right now doesn't need any support material. This would be the surface on our build plate. We're going to build up from there. So far, so good. No support material. Super easy part to build. All right. So there we go. That's our base part. And now I'm going to blow a hole through it in order to get our camera to fit in there. I'm going to do that back here so I can see what I'm doing. Got rid of the rest of the model, and I'm just working on that one part. So here I'm drawing my shape. This is the shape that I want to knock out. I'm going to snap it to the origin in order to make it symmetrical across the origin. And I believe that that camera is 19mm wide, so I'm going to type in 19mm there. All right, we can pop that there. And I want to give it some sort of thickness down here at the base. 3, sure, let's say 3mm down there. And we're going to cut all the way through with that sketch. Through everything, right through. Cool. That's kind of our amount. We're going to need like a screw hole for our tiny little screws to mount into. I'm gonna just assume for right now that those are M2. Don't need head clearance, we just need a straight hole. M2. Normal. Through the whole thing. Position. I'm going to snap it to the center of that circle. There we go. 3D printer should be able to print that hole with their layers going horizontally here without any support material going in there. It won't be super clean, but it can do it. That's not a problem. Okay, so there's the beginning of our camera mount. Not too bad. You know, Smarky, we can print the camera mount out of pink TPU. Do they make pink TPU? Maybe that'd be a good present for Smarky. Our board doesn't have enough clearance on that part, does it? No. Let's go to a cutaway view, see what's going on here. Okay. So we're just kissing the bottom of that camera mount. That's not ideal. This is definitely not going to let anybody run a shallower camera angle. You're going to be forced to run this angle or more. Let's look up that angle. I forget what it is. It's been a while, but we did set the angle. What is it? Angle 40 degrees. So that's a 40-degree camera that we got set up. 40 degrees of up tilt. So anybody that likes to run 10, 20 degrees, this isn't going to work. So let's see if we can fix that. First things first though, I'm going to lock this part in place because right now it's free to move around. So I'm going to grab the two faces that are supposed to be touching and mate them together. I'm going to use the front edge kind of as a reference. I'll mate those together. Now we just have to take care of left and right. And to do that, I'm going to take this part, grab the right plane of that part, and I'm going to take the right plane of the assembly and mate those together, and now we're fixed. Can't go anywhere. Sweet. Alright. Camera's still movable. So my camera, I'm now going to lock in. I'm going to take that hole and mate it to that hole. And now she's fixed. Okay, cool. Now, let's go back to our part, and we're going to make this part adjustable so that we can find the correct height that we're going to need. Back to my original sketch. There we are. We're referencing that front edge in the assembly, so right now this sketch is kind of floating in space. I'm going to lock the front corner. So that's like our reference point. Can't move. Okay? Those are fixed. And I'm going to start dimensioning this part. So 23, let's round that up to 24. And the other important thing is going to be this whole location, because that's our camera mount. So I'm going to take a dimension from here. Say, okay, 12.5 millimeters back from the front edge of the quadcopter, and the height, so from the carbon fiber frame up, 13. 13 millimeters was not enough. We were still bottoming out. So I'm going to take that up to 14 millimeters. And this last measurement, let's just say that's 2. That one's not as critical. Okay. Save that part. Back to the assembly. How are we doing? We're an hour into our live stream. There we go. So now I gave it some more room. Let's go to our cross section. I added an extra little millimeter in there, and now that board's got a little bit of room to swing. I'm curious just how much room does it have to swing. I'm going to delete that angle. We had it fixed at 40. Now this part is free to swing. And let's see. Works will let me grab the part. There we go. At 14 millimeters, the board clears. So you can run flat. You can run like 10 degree, which is like, that's about how fast I can fly these days. And you could be like digital silence and pretend that you know how to fly like this. Yep. It's fun until you got to get through that first gate. Or land. So anyways, that's looking good. 14 millimeters tall. Beautiful. Alright, did I install Cure on this machine? I think that was something I wanted to do, and I did not. Okay. We'll have to take a look at that. And maybe we can... How long does Cura take to install? It probably doesn't take too long to install. Get that going on this machine so that I can show you how to set up the 3D print. We should probably make it look prettier. Right now it looks pretty utilitarian. Kind of ugly, right? Need something better looking than that. Hmm. Good thing. Maybe we can extend something off the front, protect the lens a little bit more. Right? We can kind of give ourselves a couple of fingers off of here. I think we need to round this corner off because see from the bottom of the frame poking out, overhanging a little bit. I don't like that. I say we make it. How wide is this frame? 25. Let's make this thing the full width of the frame. That looks a little bit cleaner. 24. Let's take that up to 25. And update. There we go. That's kind of flush. I think as long as if we round that edge over, we'll be in good shape. All right, a crown in the side. I'm done with the crowns. We already got a crown back there. I guess we could put a crown. We can emboss a crown into the side right there. We got plenty of room to draw right there. We probably have more material than we need. I'm thinking. I want to see what this looks like as a shorter part. Like that. Yeah. There we go. I don't think we needed all that material back there. I think that was waste. How much do we weigh? Let's give her a weight. 259.9 grams. All right, we're over our 250. We have not given this a definition for weight. What is this thing? This thing weighs 2.5 grams. That's pretty light. Somewhere we picked up a little bit of weight here, though. We're over our 250. Our little sensor warning us? No, our sensor's out of date. Update. Yes? No? Update? 250? Yeah. Way overweight. We gotta find ourselves 10 grams here. A Bills logo. I can't sell it if we put a Bills logo in it. Can't do anything if I put a Bills logo in it. Hopefully we cut a whole bunch of these frames out. That's the idea. We're gonna build one, take it all the way to completion, test fly it, make sure it's good. If it doesn't fly, we're gonna fix it. We're gonna show the whole process of setting up beta flight, fly the quad, and then raffle the quad off in the live stream. Somebody in our live stream will end up with this quad, and we're gonna set up like a short production run. So the rest of the frames on the sheet, we'll buy a single sheet of carbon fiber, like let's say 2 foot by 2 foot, and the rest of the frames on the sheet, we'll like post those for anybody that wants to, buy one of the frames. Probably like throw them up on Amazon Prime or something like that, so you can just go grab a frame for a few bucks. We'll show the whole process of like nesting the frames together, getting the maximum amount of use out of the sheet of carbon fiber. And we'll show how to break the price down. We're gonna pay X amount of money for a 2 foot by 2 foot sheet of carbon fiber. And so in order to get your frame price down, you're gonna want to fit as many frames on that sheet as you possibly can. The more frames you can put in the sheet, cheaper the frames are gonna be. So we're gonna go through that whole process. Let's see. Right now I want to concentrate on this little camera mount here. We need to make this thing look a lot sexier than it is right now. Let's see. We can make this hollow too. So we can save some weight there. I'm trying to think what can we do. Got a small idea. I don't know if it's a good one. Will it let me do this? To surface there. two. There? Yes? Okay. I'll show you guys what I just did. We had a little swoopy thing. I don't know. I thought that'd be kind of cool once I start rounding over edges. I'm gonna put some fillets on here. 1, 2, 3, 4. 4 millimeters. Front and back. Rounding over. And like a 1 millimeter. There. We're gonna start making this part look a little bit better. 1 millimeter, 2 millimeter. There, starting to look a little bit better. Round that over there. Sure. 2 millimeter. Okay. Let's see how we're looking now. All right. That looks like a little bit more professional part, right? We got some round overs there. Matches the frame perfectly. Not too bad. 716 trademark? No, I bet you we could do 716 on the side of the quad. Havelock. No, Havelock likes to represent the 716. We would probably like run 716 right on the side of this thing. Let me save that. Let's see if we can build that right into the side of the... Or we can't print? Well, let me see. Let me see what we can do. I bet you it would come out if we embossed 716 right there. 716. That. We need a better font than default SolidWorks font. Oh, and SolidWorks has just the most wonderful font interface in the world. 716 like that. Bigger. Units 3. Double that. 6 millimeters tall. Like that. There. Sure. 0.5 millimeter. There you go. Representing the 716. I think that'll probably come out in the print just fine. I think it would. Smaller? Do it smaller, not so. You know what? We don't have to go out. Let me see if I can edit that. Okay. A little bit smaller. 5 millimeter? 5 millimeter tall? I don't want it to be too small because then the 3D printer is not going to pick it up real well. Let's do that. Right there. And I'm going to do it as a cut into the material. 0.5 millimeter deep, and I'm going to draft. What draft is it's going to angle the walls in, and that's going to make it even easier for the 3D printer to get around. So drafting the walls in, 15 degrees. There she is. Little engraved 716 inside of the camera mount, courtesy of the Havelock. Now we just gotta get it to the other side in a somewhat symmetrical way. So same thing over here. I don't think if we do a mirror operation, it's gonna be backwards on the other side. So easiest thing to do is probably just to redraw it. Back to our text tool. 716. And in here, our ridiculous thing. 5 millimeters tall. Space like that. Good. Made my part transparent so I can see the other side, and we'll do the same cut. Draft. Punch it in, and take a look. There we are. 716. Save that part. And back to our model. Beautiful. What do we got? 1018. Got about 40 minutes left in our live stream here. All right. I'm pretty happy with that. I think that's pretty slick. I like it. It was a good suggestion, Havelock. I like it. I never would have thought it. Let's see if I can get Cura going in the background. And I'll show us making the print file. So my copy of Cura is on my other machine. The 3D printer is hooked up to not this machine, but my other machine. So let's go grab a copy of the software real quick. Get that downloaded in the background here. Yep, I'll take it. I'll be using Cura for educational use on this one. Oh my gosh. Oh my. Well, I'm wondering if there's an easier way to do this. Do I have this in a downloads folder? I am pulling. I'm not going to show you this folder. All the stuff that BA has downloaded to his computer. And is one of those things. Cura? Cura. Ultimaker Cura. No. Oh, do I have Matter Hackers on here? Ooh, I do. Sweet. Alright, we can show it. Matter Controls on here. Alright, so I use two programs for running my 3D printer. Matter Control and Cura. Kind of each one has its pros and cons. Lately, I've been using Cura. The latest build of Cura works really good and has tons of controls built into it. Controls that were kind of missing from Matter Hackers. A couple years ago, when I started, Matter Hackers had more controls to fine tune, but now it's definitely gone the other way. Cura's got tons of ways to dial in your print really well. So anyway, get rid of that. So I would say, like, this part is ready for 3D printing. So what do we do? Let me save my assembly real quick. Oh, you know what? We didn't think about attaching this. That's what we didn't do. But that's real easy. I'm just gonna put some holes, 4 holes in the bottom of it, and we're gonna come up through the bottom and catch it with. I've got these little screws that have like a coarse thread. They're made for plastic. It's got a Torx head, real tiny. That'll be perfect for catching the TPU. You could even hot glue would probably hold that permanently, as well as 3M, like double-sided acrylic tape would hold that on there real well. Good to have a mechanical fastener in there, but let's see. Let's punch some holes in there real quick. Go to my hole wizard, and this would be like a tapped hole, but we're not actually gonna tap it. Let's say M2. Yeah, M2, just a generic M2 tapped hole, and we'll start our first hole, and the other 3 holes are just going to be mirrored. So I'm striking lines of symmetry, and I'm going to mirror across those lines. That's mirrored, and that's mirrored. There's my hole pattern. Let's dimension them real quick. Let's call that 16 millimeters there. Dimension this guy, 12 millimeters. And our depth, you see what I did there? By giving myself a little bit of material, I can have those screws go in deeper. If I wanted to, I could actually back these back holes up, get more meat. I'll do that. I think I will. Let's delete that symmetry and take a different approach. I'm going to draw a box in order to line them all up. And then I'm going to start at the front edge and dimension them from there. So 4 millimeters back, sure. Front row, what do we got here? I delete that. Oh, 12. No. 12, 13, 14. Perfect. Now I can see that I've got maximum material. Now, I might as well drill those holes all the way through, right? How's the chat going there? Boom. Drill them all the way through. No support material needed. Perfect. Like it. All right. So I'm going to save that, and we're going to export an STL file to get this ready for 3D printing. So I'm going to go up to File, Save As, not a SolidWorks part. I already have it saved as a SolidWorks part. I'm going to come down and select my STL, right, which was, that's originally like your stereolithography file or whatever. I'm going to scooch this window over a little bit so that I can see my part. And I'm going to come to the options, and here, this is the wireframe conversion of the part. All right. SolidWorks is telling me about how big the file is going to be, how many triangles it has, and I have some settings to change just how many triangles we use. Okay, so what this is doing, we're no longer going to be a parametric model. We're going to be a wireframe, and there's no coming back from a wireframe, right? It's got like a fixed resolution. So if we don't put a lot of triangles in there, you end up with a part that looks like this guy. This is like a low resolution STL file, and I don't know if you can see it well or not. Can you guys see that? But you can see the squares. Maybe you can catch the light of the squares there. So what those squares are is really big triangles, right? So when that file got exported, it got exported as kind of a low resolution. That camera gonna refocus for me? Yeah? Yes? No? Yeah. Okay, whatever. Not critical. Anyway, so if I were to turn this down, we can reduce the number of triangles in our part down there. Now we're at like 5,000. We can get even lower. Now we've only got 3,000 triangles there, right? But you're going to see those facets when you go and 3D print it. You're going to see all those little surfaces. It's not critical to the function of the part so much. It's just an aesthetic thing, right? But getting the file size down real small helps your 3D printing software work faster, right? So if you're loading up files in Cura and it's taking forever to do anything, it might be because you've got a really heavy file, tons of polygons, tons of triangles in it. So you can kind of tweak your settings in here to give yourself the best of both worlds, a file that is going to look good and not have all those little facets, but a file that's not so big that it takes an hour for it to open up in Cura. So anyways, we'll kind of tune this to where we've got a decent balance of triangles. It's going to be most notable on these curves here, and that's a pretty good number of triangles. I don't think you're going to see the facets with that setting. We've only got 4,000 triangles. That's a very small file. So we're going to say, okay, that's good. And we'll save you. We'll give you a name. Let's see. Live. Woo! I'm not typing in the right place. Live stream cam mount. I have one Fender. It's on the other machine, the video editing machine. There's an i9 sitting in the machine next to me, and here I am sitting on right now I'm on a 9-year-old computer, and I've got a brand new i9 computer sitting next to me, not doing anything. But that's how it is. You know why? Because SolidWorks doesn't run on the new machine. SolidWorks runs on this machine. This machine has a Quadro card in it. SolidWorks works better on this machine. 9-year-old machine, right? Go figure. Anyways, I bet you if I had the latest copy of SolidWorks, it would work good on the new machine, but we gotta make do. I'd rather spend the money on the computer rather than spending $3,000 on a new SolidWorks seat. Where were we? Okay, so we got our STL exported. Next thing would be to fire up our printer software. And let's see. Hopefully this works without being connected to the printer. Blah, blah. Okay, add a file to our software. I'm going to go pull up that STL. Oop. Okay, there she is. This is the build plate for my machine. And like we want to reorient that part onto the build plate so that we don't have any support material being generated, right? So I'm going to edit this, rotate it. I have no idea which one of these buttons is going to be the right one because there's no like reference axis in the corner, but I'm just going to hit one and see what the heck happens. This part. I guessed right. There we go. So I've rotated the part. Now it sits flat on the bed. That's the orientation I want to print in. Not going to require any support material. Super easy. So I'm going to save that. And the next thing we're going to do is slice it. So I'm going to bring up my settings and controls. Oh, can you guys see that? There's a little camera in the way. Let me reposition my window here. Make this a little bigger. Okay, do that. Hopefully that looks good. Okay, there's our part here. Basic controls here. You've got your layer height. That's going to determine the part resolution, the time it takes to build. The lower value there will give you a better looking part, but take exponentially longer to print, right? So a build height of 0.1 millimeters is going to look awesome, but it's going to take 3 times longer to print than something that's got a print height of 0.3 millimeters, right? So I'm going to say 0.3 millimeters. The looks aren't as critical as the strength, right? We want a strong part that doesn't take too long to print. Our first layer height, that's going to be fine as well. Outer surface, perimeters. Okay. That is going to be the outer skin of our part. That's how many times the 3D printer is going to go around the outside and to build the outer wall. Having that number set to 1 is going to be your fastest print. With your if we're printing this out of TPU, that's going to give you your spongiest part. If you have some open infill, I'll probably take that to 2. I want the 3D printer to go around twice and give me a double thick wall. Top and bottom surfaces, I think same thing. I want 2 solid layers on the top and on the bottom. That's going to give me a really nice outer shell on my part. Okay, so now we've kind of determined the outside of the part and our layer height. We're going to go to infill. That's what's the 3D printer going to lay down on the inside of this part. Here's our fill density. That's our first value here. 0.5, that's a percentage. So 50% infill, right? It's going to be half air and half material. That is probably higher than it needs to be. Let's say we do 20% infill. So mostly the inside of this part is just going to be air. Instead of lines is good. This infill type is the pattern that the printer is going to lay down on the inside. Lines is going to be alternating 45-degree lines. Grid is going to be a whole entire grid. You got triangles, hexagon, concentric circles. Grids and lines is basically what you're going to use the most. In Cura, they have some more advanced options, which is why I've gone over to Cura now from Matter Hackers. I like to use these variable infills that are denser in certain areas and lighter in other areas. Our angle of our lines, yes. Infill overlap, that's going to be how much penetration there is between the outer walls and the infill. You want to make sure that they overlap just a little bit so that they're nice and secure. All right, our speed. These values you're going to get from your filament manufacturer, right? So, like Smarky, I think was saying earlier in the Facebook group that he's printing TPU at 70, which I think is nonsense. He's not. There's no way he's going that fast in TPU. But anyways, this is where you're going to fill out your speed for your filament. You can set different speeds for different layers. You may want to start the print slow so that it sticks to your build plate really well. And then as you go up, you're going to increase your speed as you go up. Top solid infill. If you top solid infill. Top solid layers. Okay, I think this slowing down there might help hide your infill pattern on your top surfaces. Speed for perimeters. Okay, so how fast it goes around the outside, how fast it does your support material, how fast it does bridges, how fast it does travel moves, and how fast it does the first layer. Okay, modifiers, first layer speed. So first layer is going to be 30% of regular speed. So it's going to be nice and slow on the first layer. That's going to help it stick to the build plate. Rafts and priming. If you're having adhesion problems, you can print a raft first. A raft would be a fairly large flat part. That's going to help like glue your part down to the build plate. After it prints the raft, which is just only a couple layers thick, then it'll print your part on the raft. And because your raft and your part are made out of the same material, they're going to stick really well. You won't have any problems with the part popping off of the raft. For a part like this, it shouldn't be necessary because we've got a nice flat base on that part. It's going to stick to our build plate really good. Priming loops. You want to do a little bit of a priming loop because if you ever use like a hot glue gun, the first couple pulls of the hot glue gun trigger and you don't get any hot glue out, it's the same thing with the 3D printer. It needs to just kind of like draw a circle around the part in order to get the filament coming out the nozzle. If you don't prime it first and you just start printing, you'll notice that the print head is going to go around a couple times and nothing's coming out yet. And then materials start flowing after you're, a couple minutes into your part there. So that's your priming. First layer expansion loops. I think that would be a brim. It's called a brim in some of the other ones. I like using a brim on PLA and ABS. TPU doesn't need a brim. The TPU seems to stick to my build plate more than well. It's actually hard to get off the build plate. Okay, support material. I said if you were printing this part in like a different orientation, you would need to put support material underneath your overhangs. Otherwise, the printer doesn't have anything to print on. It can't print in dead air. The filament's just going to fall to the table. So you always have to print support material. The way we designed this part, support material not needed. I can turn that off. Output. The rest of these, we don't have to worry about. Okay, filament. This would be what we're printing it out of. 1.75 millimeter. Yeah, PLA. That doesn't matter. Temperature. This is critical though. Again, refer back to your specs that come with your filament and determine what your extruder temperature should be and what your bed temperature should be. I don't think the TPU needs a very hot bed. Let's say you run like 60 on the bed and like 240 degrees on the head, right? So that's probably more of an ABS temperature. But anyways, you're gonna want to look up the correct temperatures for your for the material that you're using. I don't know if Smarky, if you're in the chat, do you know what your settings are for TPU or Ben, I know you guys have been printing TPU lately, right? Off the top of my head, I don't know what the temperatures are. Anyways, that's where you would set them up. Retraction. What retraction is, going back to the hot glue gun thing. When you're doing hot gluing and you let go of the trigger and the hot glue just keeps flowing, the retraction, the 3D printer, it's basically a CNC hot glue gun, right? So when the 3D printer stops extruding, material is going to still keep flowing out. What retraction does is it pulls the material back. You know, like if you ever took the back of your hot glue gun and pulled the hot glue stick back a little bit so that it quit spilling out all over your table, that's what retraction is. Extrusion, this is like fine tuning your extruder. If you're having any kind of a problem and you need it to extrude faster or slower. Cooling, that's going to be how much fan you're using. If you're using ABS, you probably won't be using much fan or any fan at all. If you're using PLA, you're going to use like 100% fan, and that's to make sure that your part is cooled so that it doesn't start like deforming from all the heat. ABS can take a higher temperature, so ABS you would normally run no fan. That way you've got good layer adhesion, and your part isn't shrinking from cooling too fast. PLA doesn't shrink that much compared to ABS. So your PLA, you can hit it real hard with the fan, get the part to cool down, and it'll hold its shape better. Anyways, settings that you kind of, those are fine-tuning things. You know, you print a part and, you know, all the walls are kind of lazy looking, and you might turn your fan speed up. My printer, that's not connected right now. Anyways, so let's preview our slicing. So we set up our settings. I'm going to go to layer view, and we're going to generate the G code to run the printer. Okay, and I can run through my layers and see exactly how this thing is going to print. Let's see. Speeds, there we go. That's what I want to see. So here's our first layer on the bed. You can see the priming loops around the outside. And you can see that our speed is fairly slow at 18 millimeters a second. And then we can go up a layer. We can go one by one. We got 60 layers it's going to take to print this. Here's our next layer, and we're ripping at 60 millimeters a second. That's full speed now. And you can see we set it to be 2 layers thick for the outer shell. So layer 1, layer 2. Then the next layer is going to be infill. So there's our infill, which is lines. And you can see the shell still has two perimeters, right? The head went around 2 times around all of our outside walls. And this is what 20%, right? 20% filament looks like. So yeah, 20% filament. And you can see that the lines alternate, which is, it's nice. It's faster than printing grid. Grid does squares across the whole entire thing. Lines alternates. You still end up with a grid, but it's twice as fast because it chooses to alternate the direction from layer to layer. Anyway, hopefully that makes sense. So anyways, here we go. We're working our way up the part. You see the infill going back and forth, and our walls closing in. Okay, that's it. Now it's just printing those 2 support columns, and it's working its way up. And then you'll see the hole for the camera mount develop as we go up. Up. There's the hole. There she is. So that's our hole where the camera's going to mount. Then you'll see it close and boop up to the tip. All right. Without printing it, we can see. That helped illustrate what's going on. You can see the 716 in the side of it. Somewhat. It's there. You've got a 17-minute print time. That's totally cool. You can see that we've used under a meter of filament, and we've used, this is the easiest one, 2.3 grams of filament. That's interesting. Estimated mass, 2.3 grams. What the heck did SolidWorks say this was? 2.8 grams. Not bad. SolidWorks thinks that this is a solid part with no infill, and it's calling it 2.8 grams. This has infill, so there's air inside of it, and we're estimating 2.3 grams. You're really in the ballpark. I mean, you can estimate the weight of your build pretty darn close. I mean, you're usually within the weight of your wires, you know, because we're not modeling the wires. But anyways, that's how you set up the 3D print. What I'll probably do is do the same thing in Cura. I'm gonna go throw it on my other machine, and I'll print that out, and we'll actually have that for the next live stream printed out. See, that's good. Close that back down. That's 3D printing. Not too bad. What gets funny is when the 3D printer is fighting you, and none of the settings want to work, and you're constantly scraping bad prints off the build plate. Then it gets frustrating. But I don't know. Instead of screwing around, first thing you do, go right to the manufacturer, see what their recommended temperatures are, see what their recommended print speeds are, and start there. The best way to go about it. All right, we got about 15 minutes left. Rather than take care of that, let's go over and look at machining the frame out. Let's do a little CNC programming. Okay. Let's say our frame is done. Oh, actually, real quick, we got one more hole. Another set of holes to punch out. Camera mount, frame. I'm going to isolate these two parts. There we go. I need to drill holes in the frame to accommodate those screws. So I'm going to edit this part. I'm going to edit it right in context so I know exactly where I need to drill those holes. All right, hole wizard. There we go. This is a clearance hole for a screw. No. Let's do a countersunk. Just like here. That way we're not interfering with our battery. Okay, it is not inch, it's metric. M2. Loose fitting, that's probably fine. Position, I need to see through my model. And my mouse stinks. Oh, so I'm snapping my points in context to the other part. That makes everything go super fast. Go. And if I want a little bit more countersink, I can come over here to head clearance, give myself just a touch, half a millimeter more. There, I think that looks good. Okay, back to the normal view. My fasteners should go right in there. Like I said, I've got these little torque screws that I think will grab onto that print really good. Marty, where you been hiding? Everybody, Cram Knit Rams here. How long have you been in here, Marty? You know what I need is to figure out a little display. I got a monitor over here, monitor over here. I actually have a laptop over here. So I've got 3 displays in front of me, and none of these displays have a really good way of showing me who's in the chat. So every once in a while I get a little surprise. Like Marty. Little Marty surprise. I should do a time lapse. Marty, the thing with the printer time lapse is that my printer has the moving bed, right? And so the time lapses usually look ridiculous because the parts moving all over, so it's all blurry. The printers that have the fixed bed do way better time lapses because you can see the part grow. And I know that the 1 3D printing guy on YouTube, he actually rigged up a what did he use? He used a camera and a Raspberry Pi and the machine vision so that it only took a picture when the part was in the correct spot. And so his time lapses look really good. But I'm not doing that ever. So I don't know. We'll see. Okay, exit isolate. All right. Good enough. Stop editing that part. I'm going to save my assembly. I think my computer's getting hot. All the fans. It sounds like there's a jet engine taking off in here. All right, let's open up that frame and get it ready for cutting. This is still a virtual part in the other assembly, so I need to save it as a real part. 4-inch stream, right? Schmarky's here. Okay, I'm going to make a new assembly from this frame, and you're going to see why in just a second. Okay. An assembly is for putting multiple parts in. My router works on the top plane. So I'm viewing the top plane right now, and I can't see my frame. So I'm going to rotate the frame so that I can see it from the top view. All right, grab my top plane. And smack it down like that. Okay, top view. There we go. All right. Let's take a look at sheets of carbon fiber. Oop. Carbon fiber. Here we are over at Dragon Plate. One of the sources for carbon fiber in the US. This is good carbon fiber. It's on the very expensive side of things, but it's very high quality and it's extremely strong. And you got a lot of choices what kind of carbon fiber you want. It's not just thickness when you're talking about carbon fiber plate. There's a ton that goes into it. A lot of the cheaper frames, you know, your $20, $30 frames are going to be made out of like what they're calling economy carbon fiber. It's nothing fancy. It's mostly fabric laid up. The carbon's fairly heavy because it's got a lot of epoxy in it and not a lot of carbon fiber in it. And it's not terribly strong. And it's a bit more flexible than the good carbon fiber. All the frames that I cut out are out of the quasi-isotropic carbon fiber. And what quasi-isotropic means is that the fibers go in many different directions in order to give you even stiffness in all directions. That's, I think, the simplest way I can put that. I have not messed around with the foam. I've been thinking about like the birch core. I kind of like the idea of the birch core carbon fiber. And what Fender's saying is, he's asking if I've ever messed around with foam core. They sell carbon fiber sheets that have a layer of foam laminated in the middle to make them even lighter. And as long as you don't need the strength of like all 4 millimeters carbon fiber, you don't need all that strength. What you can do is fill the center of the lamination with foam, save a ton of weight, and you still have a lot of strength because most of the work is done by like the fibers that are closest to the surface. I was thinking that um, that the birch core would kind of be a really good balance between weight and still be fairly stiff. Yeah, yeah. Matt says it's expensive, and he's right. It is expensive. I mean, you're getting into like aerospace stuff, carbon fiber sheets with core. Here you've got all the different core materials that they laminate carbon fiber to. And some of these are trademark names. There's like honeycomb materials and different types of foam, birch, balsa, foam, honeycombs. There's like Kevlar and stuff like that that you can get on the inside of it. It's expensive, that's for sure. But if I just pull up a sheet of something I like, let's say we go into the quasi-isotropic. When you look at a sheet of carbon fiber, the cloth woven look of the carbon fiber, let's see. Let's see if I pull up my little scope here. Scopey scope. There we are. So that stuff, the woven fabric, that is only the very top surface of the sheet of carbon fiber, and it's just there for the look of carbon fiber. There's a reason for that fabric, and the reason to use that fabric is if you need to get the carbon fiber to conform to compound curves, it has to be a woven fabric like that. But as far as sheets, flat sheets go, you don't need fabric like that. It's purely there for the aesthetics. Let's see if I can get a shot of the edge. There's the edge of the board. This is a sheet of the quasi-isotropic, and you can see the layers. That is unidirectional carbon fiber inside of there. So there's no cloth in the center of this lamination. All these fibers are unidirectional, which means all the fibers all going in one direction. It's not a woven cloth, right? But each layer, and you can see the layers, you can see the striation there. Each layer, they turn the direction of the fibers. So there's like your first layer, let's call it 0 degrees, and then the next layer is at 45, and then the next layer is at 90, and then so on and so on. And they build the sheet up, and they change the orientation of the fibers on each layer. And when you're done, you have a sheet of carbon fiber that is like equally resistant to bending in every direction. You could also get like unidirectional carbon fiber sheets, so that all the internal fibers were all running in one direction. So that would give you a ton of strength down the length of your arm. It would not bend at all, but you would lose the torsional rigidity. So it'd be easy to like twist your arm if you did that. Anyways, tons of things you can do with carbon fiber. It's not just how thick it is. So anyways, let's see. Look up a plate real quick. Quasi-isotropic. I like that. That's a good sheet. I'm going to come down here. 3 millimeters. Actually, we were looking at 4 millimeters, right? Let's see. Let me find a 4 millimeter sheet of carbon fiber. Economy 4. Whoop. Economy 4. So this is their cheapest carbon fiber. And cheap is, of course, a relative term. All the sheets are woven material. Well, this sheet here, this this one that I have, it's not, those internal core layers aren't woven cloth like that. They're not like a twill weave or anything like that. There's a like a binder to keep them all in the right orientation, but those fibers are all running in one direction. I think sometimes they'll, like every inch there'll be like a thread that like goes across, but you know, I suppose that's kind of woven. Let's see, where's my desktop? There we go. Here's our 4mm, our cheapest economy carbon fiber plate. I just wanted to kind of get an idea of price. Let's say a 2 foot by 2 foot sheet, right? So economy, 4mm, 24 inch by 24 inch. There you go, $242 before shipping. Let's go off of that sheet. Let's assume that we're gonna get this sheet, and that's what we're gonna make our quads out of. I wouldn't use this sheet because it looks really good and sexy on the top, but the bottom of the carbon fiber sheet just has the texture of the whatever it is, the thing that they used, not vacuum bagging, but whatever the other plate is, just has like a goofy texture in it. What bit am I using to cut the carbon fiber? Marty says I've got that sitting right next to me. Anyways, 24 by 24, 250 bucks. I'm gonna come back to my assembly, and I'm gonna draw a 2 foot by 2 foot square as a reference for that sheet, because I want to see just how many quads I can fit on that sheet, because I got 250 bucks out of my pocket, right? So if I only get one frame out of that sheet, that's a $250 quad frame. So I'm gonna want to stuff as many quads as possible onto this sheet, and so I can start pulling these off, and we're gonna try to find a really good pattern here. This would be the dumb way to do it, I'm gonna say. Let me see how many quads I can get to fit like that. All right, this is really terribly nested, and we're gonna see how many sheets I get, or how many quads I can get. Very bad. Okay, so that was a really crappy job nesting it, but I want to illustrate where we're going with this. I've got 250 bucks out in that sheet of carbon fiber, and I have 9, 10, I've got 11 quads on there. So 250 bucks divided by 11, $23 each just in material alone, and we haven't even started machining these things yet. Marky says, what are we doing for a top plate? I don't know if we're doing a top plate. I suppose, you know, we should, but I kind of wanted to get to some CNC programming, and then I'm going to wrap it up for tonight. And so I can go back and we could do a little bit more detail work next week, although I might want to actually like start cutting these out. Hopefully I can live stream actually cutting one of these frames out next week. That's the plan for right now. Anyways, back to where I was here. We're looking at 11 parts, 20 some dollars a frame. That's no good, right? We need to be competitive with this stuff. So we're gonna try really hard to fit a lot more quads on this sheet that we paid a ton of money for. And I don't know if we're gonna get that many more on here or not. Let's see how much room we can make. It's gonna be tight. Tight. Oh, we're making room. We're making room. Yeah, we're getting some more quads on here. You need a little bit of margin because we got to make room for those cutters to come around. But I think you get the idea. Every time we add a frame here, the cost of these things goes down. Can we get another row? Oh, so close. So close. We only added one more frame. Yep. Nesting is wonderful. I am positive that we could fit more on here. There's still a lot of sheet left. But anyways, I don't think we need to do that just right now. And what we can start with. Anyways, what you'd want to do is you want to spend some time nesting, especially if you're going to make a lot of frames, because this is where you can save a ton of money, getting the most out of your sheet, least amount of scrap. Let's go back and I don't even know if we have to save that. What we're going to do is export this frame over to the program that I use, which is Mastercam. I use Mastercam for setting up my CNC routers. So I'm going to show you real quick. Let's see, 11 o'clock. I think we're still doing all right, though. 2 hours in. Let me get to this real quick. Save as. This is going to be a DXF. DXF is my preferred way to make a router cut, a simple two-dimensional router cut part. This is the easiest way to do it. I'm going to export a DXF. The DXF is basically a drawing, just like a shop drawing, engineering drawing, whatever, blueprint. It's just a single view, and I'm going to come over to the views to export, and I'm going to export top view. No, not the top view. That's the top view. Which view? Front view. I'm going to export this view, which happens to be the front view. And it's going to show me the output. Yes? Yep, there she is. Okay, so it's telling me that's what it's going to look like. Yep, that's exactly what I wanted. Real simple, just the outlines. Doesn't have to be a three-dimensional model. Although I can import a 3D model, there's really no purpose to, because I don't have like multiple levels. I don't have pockets. I don't have curved surfaces. There's nothing crazy here. Super easy part. So I'm just going to export myself a little two-dimensional DXF and then head over to Mastercam. So let's see. Let me adjust my screen. Here we go. Here we are over at Mastercam. This software I'm not going to get into too much depth with because it's going to be real specific to the exact machine you're using and whatnot. And there's better stuff out there. It just happens to be what I use. I'm going to come over and I'm going to select my machine type, which let's see, we're going to run this on the Shop Saber. So I'm going to pull that up. That is going to pull in the properties of my machine. So now Mastercam knows how fast my machine can go, how big the bed is, and yada, yada, yada. I'm going to come into my stock setup. This is my material that we're going to be throwing on the machine. I'm going to define the origin of the piece of carbon fiber plate to be the lower corner. All right, this is I usually stand here at the machine, and I usually like put the origin that's like 0, 0, 0 in the side of the machine closest to me on my left. That's where I like my origin, and all the positive numbers are away from me and to the right and up. Okay. I'm going to choose to display a wireframe. I'm going to type in the size of that sheet, 24 24 inches. And does this understand conversion? Yes. So I typed in 4mm. Mastercam did the math for me. You don't even have to think anymore, right? It did the conversion to inch. That's 0.157, blah, 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 blah. Okay. Yep. Yep. See it, right? Just wondering where my stock is. Ah. I don't think my little mousy thing's working. Mastercam. Anyways, let me keep going and we'll see if anything's happening. Want to bring in my DXF file that I created in SolidWorks. Stream DXF. Open. Okay. Front. No. Mastercam not like having dual monitors or something set up. Ooh, maybe I can't stream at the same time that I'm in this program. That would really stink. Oh, you know what? I might have to pre-tape this. If it's not gonna cooperate like that. That'll stink. Yeah, the viewport's not updating. What if I put it on my other monitor? Here? Nope. Back over here? Nope. Okay, she's not happy. Alright. That's no big deal. Maybe I'll pre-tape that and we can run that next week. Let me go grab some of these cutting tools that I pulled out. I went out to the shop and grabbed some of these. This here is the cutter that I like to use for cutting my carbon fiber plates. I've got both 1/8 inch and I have 16th inch. Probably can't see it up there, so let me bring up the microscope. Oh. That is the cutter I use for cutting carbon fiber. You can see it's like a diamond ground end mill, right? It's serrated, super sharp, but it doesn't have flutes like a drill bit or a traditional end mill, but yet it's not quite an abrasive cutter. It's kind of halfway between an abrasive cutter and an end mill. Solid carbide, right? This one, I would say that's probably about a 1/4 inch, 3/8, probably 3/8 deep this can cut. It's got an 1/8 inch diameter, and this is, I believe, called a fishtail. I'm referring to the very tip of the cutter. Doesn't have a drill point. Let's see if I can do this with 2 hands. Right, it doesn't have a flat bottom like an end mill. It doesn't have a drill point. It's got this thing called a fishtail, and what that does is it cuts the carbon fibers nice and cleanly when you're plunging into the sheet. Gives you a really good edge when you're entering your sheet straight down. And they're cheap, right? I get these Performance Micro Tool. That's where I get these from. emtnow.com. They're super cheap. When you're cutting carbon fiber, super important to have ultra sharp cutters. I want to say these are like $15 a piece. As soon as they show any signs of dulling, right in the recycle bin. you don't cut carbon fiber with a dull cutter, or you make a mess out of really expensive material. They're made like, depending on what mindset you come from, you get attached to your tools and your drill bits and you'll have this drill index for your whole life. I have drill indexes from my grandparents and stuff like that, but you can't have that mindset when you're running the CNC machines. These things were only made to cut so many inches and then garbage, right? So here is a 16th. You can see this one has been used. It's got some carbon fiber dust down there. That is my 16th. The 1/8 inch is really good for doing most of your work, because if you plunge with the 1/8 inch, it gives you a perfect 3mm clearance hole without any additional work. If you need to do a M2 hole, then you need to grab one of these 16th cutters, and you plunge in or you helix in, and then you just wobble the cutter a little bit to give yourself that perfect 2mm hole. There's the same thing. It's an 1/8 inch shaft, and then it's neck down to that 16th inch. About a 1/4 inch of teeth on there. And let's see what else I've got. Oh, this one's cool. So this is it's kind of like a hogger, but same thing. It's made to shear those carbon fibers nice and clean, right? So it has flutes like a regular end mill, but they put those super sharp serrations on it like a hogger, and so you can really crank through carbon fiber sheet with this cutter. 1/8 inch cutter, again, it's got that fishtail cut on the tip, so that if you plunge in, it'll do a really good job at shearing the carbon fibers as it goes in. And the helix here, those flutes give you really good evacuation of the dust. You don't want to make dust when you're cutting carbon fiber, but you don't have much choice. You can't develop much of a chip in the carbon fiber. The goal is to make a chip, and when you're in the sheet, a lot of the YouTube videos I watch of the guys that cut carbon fiber drone frames on their desktop CNCs, they're all going way too slow, and all that does is make dust, and the dust gets into everything. It gets into your bearings, gets into your motors, gets into everything, your lungs, everything. Carbon fiber, you got to wear respirators and stuff like that. If they crank up their speed, I mean, it takes some balls, but you got to go, right? You got to rip through those sheets. And then you don't make dust. You make a little bit of a heavier chip, and it doesn't get all over everything if you run your machine at the correct speed. There's definitely not a lot of information out there about the correct feeds and speeds in carbon fiber sheet, so it is a bit of trial and error. I do all the cutting dry. Havelock was asking if I use coolant. I don't use coolant. Like the epoxy resin that the sheets are made out of aren't compatible with very many things. You can do water. I've seen a really cool setup where they build a bed and sink the carbon fiber sheet in like a little pool of water, kind of like, I don't know. It's kind of like your plasma cutter, the sheet's up above the water. But anyways, it would be cool to build a table so that you could do the carbon fiber underwater. Then you wouldn't have any dust to worry about. You just have to worry about what you do with the water after you're done cutting. But as long as if you move quickly through your sheet, then you don't make so much dust, and it's not so bad. what else do I got in my little kit here? Here, as long as I've got a microscope, I can show you some other cool tools here. Let's see what this is. Here's a ball end mill, and it's so tiny I can't find it. There she is. Okay, so there's a ball end mill. That's an 1/8 inch shaft, and there you can see the ball at the end of this mill. It's a 2 flute, and I do this for doing super fine detailed like relief, right? So like a 3D. I've used this to cut out like little terrain models, little scale terrain models, and like coins and things like that, where you're in there doing some super detail work. The size of this is 20 thou. That's the size of that ball. So 20 thou ball on the end of that one. Very cool. And let's see. On the other side of the spectrum, we kind of have the like supersized version. I don't even know. Can I fit this under the microscope? Much here. This is 2 flute. This is a big hogger here. It's got the serrations on here. I use this guy for doing hardwood and urethane foams, and it's probably better on the regular camera. Let's see here. That's our 1/2 inch hogger. I don't know if you can even see that well, but up close, up here. There we go. So 1/2 inch hogger does wonders in hardwood. And here's another guy. Similar, I use this one for really deep cuts in foam. 1/2 inch, and I think like a 4-inch flute length. 4 inch cut length. Very cool. Shatter City with this one if your feeds and speeds are wrong. But I don't know, it's fun stuff for cutting the tooling board, urethane boards and stuff like that. I don't know. I'll have to figure out a project that we can use the urethane board for. But like for Smarky's little project today, we were casting the silicone. But one of the other things you can do is actually machine the mold out of tooling board rather than casting silicone. I don't know. We'll have to come up with a good project for that. That's another thing you would use the ball end mills for. I think that'll do it for tonight. I don't know, 2 hours, 20 minutes in. Not too bad. I will probably pre-tape doing the CNC programming in Mastercam because it looks like Mastercam. Some of these CAD programs are very picky about video, and it doesn't seem to want to work and live stream at the same time. I might have to pre-tape that somehow. I know I can't use Mastercam or SolidWorks on my newer computer because the resolution's too high. And these programs, they won't even open with the resolution that high. It's ridiculous. It's a real pain in the butt. I have to go back. This monitor has a 1920 by 1200, and the CAD programs work fantastic on it. On the other monitor, the resolution's higher. They don't work at all. It's terrible. So I'll pre-tape that. Other than that, anything else, you guys? Anything else going on that we should talk about? Or we're probably good for tonight. Like I said, most of you guys are registered to help out on the bando. Let's see, Marty, Cram Knitram, he's working on timers. He's working on additional track timers. Like we've got the one Immersion RC track timer. Marty's going to build us a couple more. I ordered the PCB boards for him. We're going to do a couple Delta 5 timers. That's going to be really cool because with additional timers means that we can start measuring people's speed on the track. And I think that's going to be an awesome thing to, what do you call it? It's an awesome statistic for you guys to be tracking. We're going to see just how fast Havelock is ripping down the like back stretch. Because once you have that second timer, all you gotta do is go out there with a tape measure and measure the distance from timer to timer, and then the computer will tell you how fast you came through that section. It's gonna be awesome. So I'm excited for additional timers. We need tons of timers for the bando. You know, a couple months away from the bando. Tickets are on sale. You guys are like volunteering and helping out, which is awesome. Marty's building timers. I got a whole bunch of stickers the other day. So on Sunday, I'll hand out a bunch of this stuff. I got all kinds of cool stickers, square ones, die cut ones. I'm not going to tell anybody what the track is going to look like on Sunday because Sunday is our championship race. I believe Quest is going to be there as well. So yeah, nobody gets to know what the track is. It's going to be, you know, a first time for a new track. Everyone's on the same playing field. I have my sheet printed out of the for the season, so I know how everybody did. I think it's no surprise to anybody who's in first place right now for the points for the season. But you guys, it's gonna be cool to see second, third, fourth, fifth, and so I don't know. I've got some stuff to give you guys for doing good this season. We should probably do something for Red October, because he's doing great. He's our newest pilot. Everybody's going for second place, right? Yep. Unless by some crazy accident happens to what was the Benny Mac. Betty Mac. We need a good name for that stupid whoop. His little brushless whoop there. Yeah. Unless something crazy happens to that thing, everyone's shooting for second place. I don't know. It's gonna be tough, right? Havelock, Fender, Onyx, dude, that's tight. And we're gonna see if Quest has been practicing. I don't know if he's had much time to practice with moving into the new house and stuff. You know, he might be banging off the walls. I don't know. He's capable of being fast. We're gonna wish for a hex on Benny Mac's quad. I don't know. It's good. All we have to do, yeah. Anybody that's frustrated about Benny Mac, just wait till it's time to go outside, right? Benny Mac, you got to figure out what the secret formula is to the 5-inch quad, man. I want to see Benny Mac crushing JT out on the track with the full-size 5-inch 6L. That's what we need. Maybe that's the problem. Maybe the 5-inch was too slow on 4L for him. Matt Fender, IB Crazy tried to burn down Florida today. CFL. What happened at CFL FPV? I have not been following because I got a lot of things going on right now for the bando. So I don't know what happened with IB Crazy at CFL. Now you got me wondering. IB Crazy is going to be joining us in July for our qualifier. He blew an ESC going 200 miles an hour. 200 miles an hour with a wing or a quad? On a wing. That's sick. Yeah, IB Crazy is going to be with us at the Olean Airport for our regional qualifier. And we're going to be doing wing racing. So he's putting together a wing race across the runway. That's going to be epic. anybody that's not into the wings yet, think about picking up a wing, so that you can run it. He's got the inflatable gates that he's been setting up. They were set up out at the Riot. Dude, it's gonna be awesome. It's gonna be crazy because it's gonna be like we're probably gonna be dead tired from the bando, and then 2 weeks later it's gonna be time to set up the regional qualifier. And I think we have the last regional qualifier for our region. So anybody who's in danger of being bumped down is going to have to come out to our qualifier. So it's going to be a crazy time for us. Back to work, Havelock. See you guys Sunday. Yep. Havelock says see you Sunday. I think that's good for me too. I'll see you guys Sunday. Smarky, I'll see you whenever you're ready to pull this pull our first part off of our little mold here. And thanks for sticking around, guys. I'm kind of enjoying this. Not kind of. I am enjoying this. This is fun. So still a couple more things to work out, and yeah, we'll be up and running. I'll see you guys Sunday for the new track at the championship. All right. Later, guys.